Sorry about that. So you guys are failing me. You're supposed to be reminding me that I should be recording. All right. There we go. So if you remember the supply and demand model from Principles of Micro and Macro, of course you remember that, right? One of the things you'll note is that that's a static model, right? You're in equilibrium, and then, for instance, demand shifts, and then somehow you just get to this new equilibrium, right? Time is not really an element there. You're just in an equilibrium, and then snap the fingers, you're in another equilibrium. There's really no discussion of time. And one of the things that time brings with it is transition dynamics. How you move from one equilibrium to another. That is a very, very important part of this Solow model, and something that really, before the Solow model, economists had not really spent a lot of time thinking about. And so it's important as we work through this to kind of keep that in mind, right? That this is really an important contribution of not just thinking about life or economics as a series of equilibriums, but thinking about how exactly we move from equilibrium to equilibrium, right? When something changes and we have a new equilibrium, how exactly do we transition there, right? How exactly do we transition there? Probably the other most important contribution of this, not to jump to the tagline, right? Not to jump to the big conclusion, but we're going to see that the Solow model says that when it comes to growth, technology is the most important thing. And capital, which before the Solow model had been thought about as the most important thing to growth, Solow's going to argue that capital is actually relatively unimportant. And so we'll have to understand this more here as we go through the model. But these are a couple of important conclusions that kind of keep at the back of your mind as we go through this, right? That in the end, the Solow model is really going to point to the importance of technology. However, as we're going to see, it says in technology is important, but one of the big limitations of the Solow model is it says nothing about where technology comes from. So that's one of the how would you say it, ironic things about the Solow model, is that Solow says technology is crucial to growth, but yet Solow doesn't really have much to say about where technology comes from. And that's really going to be left up to future models that we talk about. But he does have a lot to say about capital, right? And so capital is going to be relatively less important, particularly relative to technology, right? That's going to be one of the big conclusions, and that's going to have a lot of implications for exactly why some countries are rich and some countries are poor, right? When we go back to the big three questions, this model is going to have a lot to say about those questions of what makes countries rich, what makes countries poor, why do some countries grow fast, why do some countries grow slow, why do we have growth miracles, why do we have growth disasters? So before we jump into the model, let me just spend a minute or two reminding us all of what a model is, right? A model is a simplified version of reality. I cannot spell this morning. We know that the real world is too complex. It is too complex for us to understand every little thing in it. We have to simplify reality. And so the way that we do that is by making assumptions. And that really is what a model, what a model is. A model is just a set of assumptions about what is important and what is not. So we try to assume away the things that are not so important because they just simply clutter our analysis. And we tend to focus on what is important, what's absolutely crucial to our understanding of the question that we're trying to address. Right? Models inevitably have to break everything into what's exogenous and what's endogenous, because that's the way they determine what's important and what's not important. Endogenous means determined within the model. Another way you can think about it is these are the things that are really important. These are the things we're trying to explain. As opposed to exogenous variables that are determined outside the model. Meaning that they're the things that we're not really trying to explain. So think back to the simple supply and demand model that you're all familiar with. What are the endogenous variables? Price and quantity, right? They're the things that are on the axes, right? Price and quantity. That's what we're trying to explain. What are the exogenous variables? Well, they're everything else that we can't really explain. Things like preferences, or the price of other goods, or the price of substitutes, the price of complements, people's income, right? Those are all exogenous to the model, meaning that we can't really explain why those things change, they just do, right? We would need another model to explain those things, right? So every model has to make a choice about what's endogenous, meaning what it's trying to explain, and what's exogenous, meaning what it cannot explain. And once again, we have to make this distinction because it's really the way that we simplify things, right? If thinking back to the supply and demand model, I can't have a supply and demand model where I'm trying to determine consumer preferences endogenously, because that is going to be too complicated, right? What determines consumer preferences? A whole bunch of things, right? That's really best served for another model, right? So if you're interested in consumer preferences, build another model, right? But for the supply and demand, we're really focused on price and quantity, right? The two endogenous variables. So obviously using models in economics is important, right? As Keynes says, Keynes says economics is the discipline of using and thinking in terms of models, coupled with the art of choosing models that best match the real world, right? And that's really a good way of thinking about it, right? Economics is a discipline of thinking in which we use models to think about the real world. But there's also an art to it. And the art is making sure that we pick models that fit facts about the real world. And so one of the things that we're going to ask about all of our models here is, do they fit the facts of the real world? Those facts we talked about yesterday, right? We talked about 7 facts of economic growth. We should be building models here that help us understand those facts, right? They should be fitting the facts. If our model doesn't fit the facts, then we have to think about, well, what's wrong? Do we have the facts wrong, right? In other words, is our data wrong? Is our empirics wrong? Or do we have to rethink our model? Okay. So probably the best way, the best saying about models, and something that you should all keep in the back of your mind whenever we talk about a model in economics, is the saying that all models are wrong, some models are useful, right? And that is very much the way we have to think about models, right? All models are wrong, meaning that there is never going to be a model that perfectly captures every little aspect of reality. But that does not mean that they're not useful, right? So when we build the Solow model here today, of course there's things that are wrong about the Solow model, right? As we go through some of these assumptions, obviously some of these assumptions are not realistic for the way the world actually is. But the question we need to ask ourselves is, of course it's not realistic, but can it still be useful, right? Can it still be useful in terms of helping us think about things more clearly by focusing on what's most important? Okay, so that's the reason why economists use models, and that's why the Solow model has really stood the test of time, right? This is still a model used intensively by economists 70 years after it was first built. Why? Because it's simple and it gives us interesting insights, right? That doesn't mean it explains everything, but it gives us powerful insights while also simplifying really complicated questions. Okay, so let's talk about the actual assumptions in the Solow model and begin to build the model. Okay. Some of these assumptions are very, very straightforward and obviously simplifying. And then some of the other assumptions, that's really where the work's being done. We'll have to think a little bit about this. First off, we're just going to assume that there's a single homogeneous good. Output, which we're going to call Y. Okay, so is this a realistic assumption? Of course not, right? All we have in our economy is one good, output. It's the perfect good. You can drive it, you can sleep on it, you can eat it, everything, right? It's everything, output. We are not going to talk about international trade in the Solow model. Once again, this is a simplifying assumption to keep things simple. So let's just forget about the rest of the world and focus on one closed economy. The Solow model is a model of perfect competition. So the Solow model does not incorporate imperfect competition within it. So you have to think about this as a perfectly competitive model, right? A perfectly competitive model. In other words, there's a large number of small firms. There's a homogeneous good, right? So all the firms are producing the similar good. Everyone is a price taker, meaning nobody influences prices. And of course, that also means zero economic profits in this model. So there is no market power by any of the firms in this model. We'll come back and talk about this, whether this is a good assumption later. And surprisingly, this assumption of perfect competition becomes crucial when we try to push past the Solow model and think about things such as where technology comes from, where innovation comes from. Interestingly enough, it's hard to think about where innovation comes from in a perfectly competitive model. Okay, in a model where there's zero economic profits, how do you pay for innovation? That's a legitimate question, right? That's a legitimate question, and that's a question we're going to circle back to in a couple of days. Okay, now we get to the more meaty assumptions. We're going to assume that we have a production function. And it's going to be the Cobb-Douglas production function that we talked about yesterday. Oops, hold on 1 second. I just want to make sure that I'm using the right notation for your book. Yes. So I'm going to begin with this production function. Okay. So alpha is between 0 and 1. So yesterday I used 1/3 and 2/3, but let's keep it more general. I'm going to use alpha here. So k to the alpha, L to the 1 minus alpha. Okay. Note here that yesterday when I had the Cobb-Douglas production function, I also had A in here, which I call productivity or technology. Let's leave this out of our production function right now. Okay, so we are definitely going to come back and add this to our production function, but to keep it simple, let's leave it out. All right, so the first time around here, we're not going to have any productivity or technology, right? We're just going to have capital and labor. This production function exhibits constant returns to scale. What does constant returns to scale mean? If you double the inputs, meaning if you double capital and labor, you double output. Why is that? Well, mathematically, you can see it's because the coefficients sum to 1. So you can, if you have a little bit of free time tonight, you can actually do a little math and show this, right? That if you double capital and you double labor, what happens to output? It doubles. Usually we're not going to want to write our production function like this, though. And that is because, remember where we're going to go here. We want to talk about a model of growth that allows us to compare different countries to each other. And so if we're really going to be comparing different countries, we want to talk about things in per capita terms. And so how can we rewrite this in per capita terms? Well, the notation your book is going to use is whenever we use a lowercase variable, that is per capita terms. So lowercase y is equal to capital Y divided by L. Likewise, lowercase k is equal to uppercase K divided by L. These are the per capita versions of output and capital. So that's the notation we're going to use consistently throughout this class. When written in lowercase, we're talking about per capita. When written in uppercase, we're just talking about levels. So if we go back to our production function, let's divide each side by L, okay, to write this in per capita terms. What do we get? Well, we can write this like this. Right? So dividing by L is the same as multiplying by L to the -1. This simplifies down to this. Or we can write it like this. Finally, we can write it like this. So this is our production function in per capita terms. output per worker here. Okay, so what is per capita output? It is per capita capital to the alpha power. Let's think about what this looks like. What's true about the relationship between per capita output and per capita capital? Remember here, what's true about alpha? Alpha is between 0 and 1, right? So what's this function going to look like? What's this going to look like? If we increase, yeah, Jordan, help me out here.
Wouldn't it like start to increase, but since it can only go to 1, then it will like level off?
Exactly. It looks like this, right?
Yeah.
Right. So in other words, when you increase the amount of capital to labor, output goes up, but it goes up at a diminishing rate, right? You increase the amount of capital to labor, but output goes up at a diminishing rate. We have a name for that in economics. Chase.
Diminishing marginal returns.
Diminishing marginal returns. Congratulations, Chase. You are the first person to say diminishing marginal returns in this class. We will only say it about 10,000 other times throughout this block, right? Because as we're going to see here, diminishing marginal returns becomes a crucial part of understanding economic growth, right? And diminishing marginal return says that as you increase K, you increase Y at a diminishing rate. Or to say this a little bit more mathematically, the change in Y you get for a change in K goes down as the level of per capita capital goes up. And as we're going to see, this is just a crucial insight into understanding economic growth across countries. Can you grow by increasing capital alone? Yes, but the effectiveness of that diminishes over time, right? So, you know, I think this is how I explain it in principle. Some of you might remember my stupid little story, but let's say that I buy 100 acres and I'm going to become a farmer, all right? The first day I'm out there just digging on my hands and knees. What's my productivity? Low. So I go to the hardware store and I buy a shovel. What's just happened to my productivity? It's gone way up, right? So when I add capital, 1 unit of capital, what's my change in output? It's going to be quite big. And the same happens as I maybe add a tractor, right? Or as I add a combine, right? The changes I get from these initial units of capital are going to be quite big. But at some level, it's just me. And if I keep on adding more and more capital to the fixed amount of labor, well, you know, sure, I'll probably increase output a little bit, right? So I'm just making up numbers here, right? 100 and 101. I'll probably change output a little bit, but I'm not going to change it nearly as much as I did at the beginning. That's the intuition behind diminishing marginal returns. This has a ton to tell us about growth, because what does this say? That countries that are poor and have very little capital actually have much more potential to grow fast than a country that's rich and has a lot of capital. Okay, and so, yeah, we're going to talk about this here in a few minutes, but that's actually going to be one of the important explanations the Solow model has for why different countries grow at different rates. Solow actually says, somewhat counterintuitively, that poor countries have more of a potential to grow fast than rich countries do because of diminishing marginal returns. Okay, let's finish up the model here. A couple of other assumptions. These are pretty straightforward. First off, we're going to say aggregate expenditure. In other words, what can you do with output? You can either consume it or invest it. So in our model here, we have no government spending. Actually, we don't really have any government in this model, which is obviously a pretty big assumption, but once again, I think it helps us kind of focus specifically on what we want to focus here. So we don't have any government spending in this model. The only thing you can do with output is you can consume it or you can spend it. Next, we're going to assume that people save and invest a constant fraction of their income. So if they don't consume, they save. And where does that saving go? Investment. And we're just going to assume that this is a constant fraction. So let's call S bar here the marginal propensity to save. Let me note here some notation that your book uses. Whenever a bar is placed over a variable, we're trying to say very clearly that variable is exogenous, meaning it's determined outside of the model. So we're not saying what determines the marginal propensity to save. We're just saying there is a marginal propensity to save, right? People save a constant fraction of their income. So in other words, what's the amount of investment? Investment is just S bar times Y, right? You save a constant fraction of your output and then you consume the rest. So if S bar is, for instance, 0.4, you save 40% of every dollar and you consume 60% of every dollar. Very, very simple. Okay, we're getting close to the end here. This is probably, maybe you could think about this as the most insightful or impactful assumption that we're going to make. We need to make an assumption about how capital changes over time. How does capital change over time? And the assumption we make is, I think, actually pretty intuitive. we're going to assume that this describes the evolution of capital. K dot is equal to S bar times Y minus delta bar times K. Okay. Remember from yesterday, what does K dot mean? That's the instantaneous change in K, right? How K changes over time. What's it equal to? Well, what increases our capital stock? Investment. So when we invest more, when we save more and we invest more, that adds to our capital stock. What decreases our capital stock? Depreciation. Where delta bar here is what we call the depreciation rate. And once again, notice that there's a bar there. So it's exogenous. We're not explaining where this comes from. We're just saying a certain fraction of your capital stock depreciates every year. So hopefully that makes some sense, right? Hopefully that's fairly intuitive. How does capital change? Well, if you invest more, that adds to capital, but the depreciation decreases your amount of capital. So there's two competing factors here. Investment adds, depreciation takes away, right? What determines that depreciation rate? Well, we're not saying. We're just saying that a certain amount of depreciation is, for instance, 0.1, 10% of your capital wears out every period, right? And so that's the change in capital. As we're going to see, this equation here is very simple, but it does a lot of work, right, in our model, right? It does a lot of work in our model. Okay, one last assumption, and this is about population. We haven't talked about labor at all. So we're going to assume here that population grows exponentially. We're going to add population growth here. So we're going to assume that population growth looks like this. Where N bar is the population growth rate. In other words, what is L bar? What is L dot divided by L, which is the growth rate of population? It equals N bar. So if we graph this, what does this look like? Well, we start off at L0, and what happens over time? Population is growing exponentially. And for right now, we're going to assume that everybody who's alive works, okay? So we're not really making a distinction between the population and the labor force. Let's just assume that everybody's alive is working, okay? So that's the model. right? That's at least the simple version of this, of the Romer model, or I'm sorry, the simple version of the Solow model. That's it. So just as a way to kind of review what we've talked about, let's go back and make sure we're clear about what the endogenous variables are and what the exogenous variables are. The exogenous variables, well, let's do that first because they're probably the easiest. These are the ones that have the bars over them, right? So this would be S bar, delta bar, N bar, right, in our initial population. And then what is endogenous? Y, K, C, I. Technically, L. So these are the things that our model can help us explain. These are the things that our model is not really explaining, but they say they're important. All right, everyone with me so far? So before we can get into the intuition of the model and talk about what this model really has to say about our three big questions about, you know, why some countries are rich, some countries are poor, why countries grow at different rates, we need to back up and do something. We wrote our production function in per capita terms, but we did not write our capital evolution equation in per capita terms. And so let's figure out what that is now. Because remember, we want to write everything in per capita terms because that's really going to be a more intuitive way to think about things. So remember our capital accumulation equation. Is this, or we could write it like that. Now, we know that little k is equal to big K divided by L. Let's put this in growth rates. Anybody remember from yesterday, how do you turn something into a growth rate if it's written in levels? To move from levels to growth rates, what do you have to do? Jordan?
Don't you take the log?
You take the log, and then you differentiate with respect to time, right? So let's do that trick. Take the log. What's the log of this? The log of capital K minus the log of L. And then we differentiate with respect to time. What is this? What's the log, the derivative of the log of k with respect to time? Little k dot k, the growth rate of little k. What's the derivative of the log of capital K with respect to time? Capital K dot k. And what's the derivative of the log of L with respect to time? L dot L or N bar. Right? L dot L, the growth rate of labor, which we know is L bar. Or we can write it like this. Okay. Now, if we go back and plug it into our capital evolution equation here, right? So maybe we can call this equation star. What do we get? Right? Okay, now, this is little k. Those are little k's. That is capital Y and capital K. How do we get rid of those capital Y's and capital K's? Well, that's pretty easy. Let's just divide the numerator into the denominator by L. Oh my God, I forgot something. You guys have to help. I made a stupid mistake. I forgot the delta, the minus delta here. God, I knew I was forgetting something. Or just to tidy this up a little bit, we will usually write it either like this, or we will write it like this. Those are usually the ways that we will write our capital evolution equation. One of two ways. Okay. We can probably already begin to see where we're headed here with our Solow model just from these two equations. How do you increase per capita capital in this model? There's really only 3 ways you can do it. You save more, meaning you increase S bar. Or you lower population growth, meaning you lower N bar. Because remember, it's per capita capital, right? So you're either going to have to save more and make more capital, or you're going to have less people per capital. Or the other thing is, you're going to somehow have to reduce depreciation. Okay, so that's the basics of the model, right? That's the basics of the model. And so this seems like a very good time to take a break, right? Let's take a break, and then what we're going to do when we come back is not really add any more to this simple model, but really talk about what this simple model says about why rich countries are rich, poor countries are poor, try to provide some intuition, right? That's missing to this point when we've just been solely focused on developing the model, okay? So let's maybe take till, what time is it? Let's do till 10:05, right? Take a break, and we'll come back and we'll talk about all that stuff. Once again, I'll leave Zoom up and running if anybody wants to chit chat. Yeah, we get some socialization here, much needed socialization probably if you're anything like me. So, okay, see you in about 10 minutes. All right. So let's jump back into this and talk about how we can solve our SOLO model. Right? We can solve our SOLO model here. So before break, we had basically come up with 2 equations. Our per capita production function and our per capita capital evolution. Let's think about this per capita evolution function. Because if we combine these, we can rewrite it like this, right? We can combine these 2 together and write our capital evolution function like this. So here we have the SOLO model in one equation. Essentially one equation. How in the world are we supposed to intuit what this equation means? Well, one thing that economists often find useful is, instead of thinking just in terms of the math, try to visualize a little bit what's going on, right? And so the easiest way to kind of, I think, understand this equation is to think about visually what's going on in what we'll call a SOLO diagram. And the SOLO diagram is just really trying to understand this equation. Specifically, what happens as the capital to labor ratio, small k, goes up. Now, notice here that our SOLO diagram really has 2 parts. Or I'm sorry, our SOLO equation has 2 parts. This first part, S bar times k to the alpha, and then the second part. So let's think about what each of these two parts look like. What does this part look like? Well, we just really talked about this a few minutes ago, right? What does k to the alpha look like as k goes up? K to the alpha looks like that, right? It looks like that. So what's S bar times k to the alpha going to look like? This. It's just going to be shifted down by a constant. So that's what the first part of this diagram looks like. What's the second part of this equation look like? Delta plus n times k. Well, this is just a straight line. That's just a straight line. Okay, so this equation can be really represented in this graph. Now, you have all taken enough econ classes to know when you have two curves that intersect, something's going on, right? So, what's going on there? We're going to call that K star. What's going on there? What's true about K dot? At that point. Yeah, Chase.
The increase in capital from investment is the same as the decrease in capital from population growth and depreciation.
Depreciation, right, right. So, once again, notice here, we have a way to increase per capita capital, which is through investment. And then there's two ways now that reduce per capita capital. One is through depreciation, but the other way you reduce per capita capital is just to have more population growth, right? And so what happens at this point is that our per capita investment is offset by population growth and depreciation, right? So at K star, what do we get? K dot is equal to 0. Meaning that investment is equal to the loss from depreciation and population growth. Okay, now, very importantly, note here that the level of output and the level of capital are growing. Specifically, how fast are they growing? Any guesses? If per capita capital is steady, then what does the level of capital have to be growing at? The rate of population. So output and capital are growing at the rate of population, but per capita output and per capita capital are not growing at all. Okay? This is what we call a steady state. We'll call this a steady state level of capital. When you get to this level of capital, you're in a steady state, meaning that per capita output and per capita capital are steady over time. So if you get to this point, what happens to your per capita growth rate? It's 0. You have 0 per capita growth in the steady state. So there is growth, right? Because output is going up, capital is going up, but you just don't have per capita growth, right? So 0 per capita growth. So it's in that sense that we call this a steady state, right? It is steady over the long term. But that's only, I think, part of what this model is telling us, because maybe the more interesting part of what this model is telling us is what happens if we're not in the steady state. For instance, what happens if we're at a K, a level of capital to labor that is not in the steady state? So let's think about this. So I'm going to redraw our solo diagram here. So there's S times our production function. And here's our steady state. So what happens here if we're at a K, we'll call it K1, that is less than K star? So what if we're in this point? What's going to happen over time? Well, first off, do we just jump from here all the way up to our steady state next period? No, why not? What would we need to do to get all the way to this new steady state? We would have to save a whole bunch and we wouldn't be able to eat, right? So we'd have to reduce consumption dramatically and increase savings, but those are exogenous in this model, right? People have to eat. And so the thing is, you can't really just jump to the new steady state because it's going to have to take time for you to accumulate that capital. It's going to take time for you to accumulate capital. So in the meantime, what's going to be true about K dot? As we can see here, at period 1, K dot is going to be positive, right? Because S times K to the alpha power is greater than delta plus N times K. So at this point, K dot is going to be greater than 0, and you grow. you're going to start growing. And output is going to grow. But it is not going to grow you immediately to the steady state. What's going to happen over time is you're going to gradually move towards K star. Right? So think about this in multiple periods. Multiple periods, you're going to begin moving towards K star. But here's the other interesting thing to note. What's going to happen as you get closer to K star? What's happening to the difference between these lines? They're getting smaller and smaller and smaller. As we get closer to the steady state, growth begins to slow. In other words, the growth of output, the growth of capital are getting closer and closer to zero. Why? Three words. Diminishing marginal returns, right? Why are we slowing growth as we get richer? Diminishing marginal returns. All that capital that we're adding is still increasing growth, but not as much as it did when we were poor. And so growth slows as we get closer to the steady state because of diminishing marginal returns. And eventually what happens? We get to the steady state. Where growth goes back to zero. How long does it take? Well, it takes a while. Those are the transitional dynamics of the model, right? Those are the transitional dynamics of the model. So you see that this is a much more complicated model in many ways than a static model like the supply and demand, right? Because a static model, you just kind of in one equilibrium, snap the fingers, you're in another equilibrium, right? A static model is more like taking a picture. A dynamic model like the Solow model is more like a movie, right? Where you have, you're filling in the gaps between here and there, right? So basically you transition. There's a series of short-run equilibriums moving you toward a long-run equilibrium, right? The long-run equilibrium is the steady state. The short-run equilibriums are where you move period by period towards getting to that steady state, okay? So this is big. In the long run, you have a steady state, but in the short run, you have transitional dynamics. And that's the value of having a dynamic model, is it really explains how you get from here to there. All right, that makes sense. So I'm not going to do it here, but I might encourage you when you look over your notes later, think about another example and see if you can walk yourself through this example. Think about if you can walk yourself through this example, where this time you begin above the steady state. Can you walk yourself through that example? I don't think it's too hard, right? But that would be a good kind of way to, see if you can talk yourself through this without looking at your notes, but talk yourself through this and convince yourself what happens if we start above the steady state, what's going to happen to the growth rate of output, per capita output, the growth rate of capital, et cetera, as time goes on. Let's do the same thing again. But this time, instead of relying on a graph and intuition, let's see if we can do a numerical example. Let's see if we can do a numerical example. So we have our Solow equation. Okay. Now let me give you some specific numbers. So let's say that S bar is 0.3. And let's use delta bar as 0.05. Let's use N bar as 0.05. And let's let alpha be 0.5. Okay, can we figure out what the steady state level of capital is? And the steady state level of output? Sure. How do we set this up? What do we know is true in the steady state? What has to be true in the steady state? Molly, I'm going to put you on the spot. What has to be true in the steady state here about this equation?
At the steady state, there has to be 0 per capita growth. So should Y star and K star be equal? Or, no, that's K dot.
Yeah, they should be equal, but K dot should be equal to 0, right? For the reason you said, there should be no growth in per capita capital or per capita output. So at the steady state, we know that has to be true. I mean, this has to be true. We have to find the K that makes that true. So let's plug in here. S bar is 0.3. Alpha is 0.5. Delta and N are 0.5. And K. We're solving for the K that makes this true. So we get this. Now it's just a little bit of algebra, right? Move this over to this side. Let's multiply each side by K to the negative 0.5 power. So those cancel out. And that becomes 0.1 times k to the 0.5 is equal to 0.3, or that. K star is equal to 9. The steady state level of capital is equal to 9. And then what is Y star? It's just K star to the alpha power, right? So Y star is equal to 3. That should be a 0.5. So that's what the steady state is, right? We've just done numerically what we did graphically, right? What has to be true in the steady state? That there's no change in per capita output or per capita capital, right? There can be no change in per capita capital or per capita output. So we just solve for the level of capital, per capita capital, that makes that true. Let's do a second part of this. What if we start at capital stock of equal to 4? What's the change in capital in period 1? What's the change in capital in period 2? Well, once again, to solve this, we just go back to our Solow equation, right? Now we know what capital is. We just have to solve for what K dot is. So once again, it's just plugging in on the right side to figure out what K dot is. So what's K dot 1? We just plug in everything here on the right side. What do we find? K dot is equal to 0.2. So in other words, what's capital stock going to be in period 1? If it was 4 in period 0, what's it going to be in period 1 now? 4.2, because it changed by 0.2. It changed by 0.2. So then we can use that fact to figure out what the change is in period 2. The change in period 2 you just plug in everything, but notice here we use what capital stock was in period 1. So the only difference is now we use 4.2 instead of 4. What answer do we get? .195. Okay. Whenever you do a mathematical problem like this, the first thing I want you to ask yourself when you get to the end of it is, does this answer make sense? Right? Because pragmatically, if you're given a question like this on the exam and you make a math error, that's one thing. But then if you make an error of intuition, that's something completely different and much more important to me. So for instance, if you make a math error and you get an answer and you say, you know what, this answer doesn't make any sense to me. Okay, I can live with that, right? I can live with that. And that's the kind of thing that's not going to receive much penalty. But if you make a math error and get an answer, and then you try to explain to me why your nonsense answer makes sense, now I'm concerned that you don't understand what's going on, right? So when you get to an answer, an end of a numerical problem like this, you got to ask yourself, does this make sense? So think about this in terms of our intuition. What did we find? K star is equal to 9, right? What was K0? 4. What should be true about K dot in period 1? It needs to be positive because we're below the steady state. So the fact that we got a positive number here makes sense. We should get a positive number because we know we're below the steady state. So where do we move in period 2? We move to 4.2. Where do we move? I'm sorry, where do we move in period 1 to 4.2? Where do we move in period 2? To 4.395. Does this answer make sense? Yes, because notice what's happening to K dot. K dot is getting smaller as we get closer to the steady state. And so that's the way you check your answer, right? Does your answer make intuitive sense based on what I know I should be finding, right? So if I know the capital is below the steady state, I better be finding that K dot is greater than 0. And I should also be finding that K dot is getting smaller over time. And that's what we've done here, right? That's what we've done here. Make sense? Okay, good. So, we only got a couple of minutes left here. I just want to really quickly, boy, we really don't have a ton of time, do we? Shoot, okay. Okay, we know we have our 3 big questions, right? Let's talk about these first 2 questions in relation to this simple Solow model. Why are rich countries rich, and what causes differences in growth rates? First off, this Solow model predicts that countries with higher savings rates grow faster in the short run, and they are richer in the long run. Okay. So for instance, what happens if S bar goes up in our Solow model? This shifts in this direction, and we have a new higher steady state. What's going to happen? Now we're below our steady state, right? So we should grow faster to get to that new steady state. In other words, y dot y is going to be greater than 0. But what's going to happen in the long run? Growth is going to go back to 0. But we will be richer, right? In other words, the level of steady state output and steady state capital is higher than before. So the Solow model predicts that countries that save more should grow faster in the short run, and they should be richer in the long run. Does this match the data? Does this match what we actually observe? The answer is yes, basically. And by basically, I mean not perfectly. Not perfectly. But yes, there is a strong tendency that countries that are richer save more. Let me show you just a little bit of data related to this. Okay. Okay, here you can see this is looking at, on the horizontal axis, the decile of GDP per capita, right? How rich a country is per capita. And then this is looking at the average savings rate in that country. And while we see it's not perfectly straight line, it is clearly true that richer countries save more than poorer countries, right? So yes, richer countries do tend to save more than poorer countries, right? To look at this another way, find this. Oh, sorry, hold on, let me find the thing I want to show you. Hold on, I thought I had it pulled up. Okay, here we go. This is the figure from your book. this is looking at the same thing, basically. GDP per worker versus the investment rate or the savings rate. And so on the horizontal axis, we have S bar, and the vertical axis, we have how rich the country is. Is it true that countries that save more are richer? Well, yes, but you'll notice there's a lot of noise in this data, right? There's a lot of noise in this data. And so let's not go crazy here, right? That savings is not the only thing that matters about whether a country is rich or poor. And we're going to have to fine tune this as we go along. But yes, savings does appear to be positively correlated with being richer. And so on that, we can say that's a point in favor of the Solow model, right? Not a strong point, not a definitive point, but it certainly is not inconsistent with the Solow model. Okay, we're running out of time here, so let me just say that we talked about one of the things that makes a rich country rich, and that is higher savings. What's the other thing that makes a rich country rich here? Countries with lower population growth should be richer. And so this is where I want to pick up this afternoon. Why exactly should countries with lower population growth be richer? And then I want to kind of talk about this. We're going to talk about this a number of times throughout class, because this is the relationship between population growth and economic growth is actually a really interesting one. And so we'll kind of talk about what the Solow model has to say about this relationship, and then we'll talk about this in more detail as we go along and try to flesh out what the real world relationship is between population growth and income growth. But we're going to stop right there, okay? So this afternoon, once again, because these are kind of grinding days, I want to try to keep the afternoon class pretty short. So we'll meet back here at 12:30, and I'm going to try to keep it to no more than an hour, all right? So maybe even a little bit less if I can somehow manage. So we'll have a short class this afternoon. In the meantime, go run some laps, do some jumping jacks, get some good food, all right? Be ready for another session, all right? Okay, have a good lunch. Talk to you soon, everybody.